Standard radiation therapy is an effective way to treat many cancers, but it isn't perfect. It kills cancer cells, but it also kills some healthy cells in its path through the body. That's just one of the reasons Mayo Clinic is bringing a new type of radiation therapy to its patients. It's called proton beam therapy, and it has the potential to cure more cancers with greater safety and help people live longer. Doctors have used radiation therapy to kill cancer cells for many years. The standard technology fires X-rays or photons at tumors in hopes of eradicating them.
The downside to the X-rays is that they pass all the way through the body.
Mayo Clinic Dr. Robert Foote says that means the radiation also kills healthy cells. This limits how much radiation you can safely give to patients because it could damage surrounding tissues and organs. But a new technology called proton beam therapy is more precise and therefore more effective. Dr. Foote and Dr. Stephen Schild head the Mayo Clinic proton beam therapy program.
A proton is one of the key constituents of matter.
They're like little bullets that can be made to stop when they hit tumors.
The way it stops in tumors is you have to aim it properly and you have to give it the proper amount of energy so it stops in just the right place.
This massive machine is called a Cyclotron. It accelerates the protons to near the speed of light and fires them into the body. Here's how proton beam therapy compares to conventional radiation therapy. The X-rays of conventional radiation therapy radiate everything in their path, structures both in front of and behind the tumor. The proton beams of intensity-modulated proton beam therapy can be better controlled in both width and depth. The technology aims the proton beams with what's called pencil beam scanning. It paints the beam back and forth through the tumor. Because the beam does not go beyond the tumor, doctors can deliver higher doses of radiation without damaging surrounding tissues.
But where you need to be very precise, where the tumor's next to something that's critical, like next to your eye or next to your spinal cord, that's where you'll have a major advantage.
Since this is so accurate and so precise, can we give a larger dose of radiation with each treatment and give fewer treatments? Can we convert a 9-week course of treatment into a 1-week course of treatment?
Proton beam therapy is particularly beneficial to children.
Pediatric tumors and tumors in children, you really want them exposed to as little radiation as possible, and this means that their body will be exposed to a lower dose overall.
Proton beam therapy, a way to target tumors more precisely to help more people with cancer live longer. The Mayo Clinic Proton Beam Therapy program will be ready for patients in 2015. It's the result of a gift from longtime Mayo patient and philanthropist Richard O. Jacobson. For Medical Edge, I'm Vivian Williams.
So hi everybody, today we have a really awesome tutorial. As you saw at the beginning, we're gonna learn about a new device which helps to treat cancer, actually help to kill tumors and also save healthy cells. So the device that they're using called Cyclotron, and the treatment called proton beam therapy. Okay, so what is a cyclotron? Cyclotron, we're gonna talk about it in a second, but the general idea is instead of using X-ray, which usually kill what's in the way until you get to the tumor, right now we're gonna use protons. And what's really special about protons, if I'm gonna draw this energy and here the energy, so in X-ray case, we're actually killing, well, this is energy, killing everything that's in the way and decay. For example, this is the skin, and here let's say it's the tumor. But if I'm gonna use a proton beam therapy, okay, I need a precise velocity and energy, and then I can make this stuff happen. So this is the skin, so there's maybe a really low energy, and then at the tumor I'm gonna have this massive peak of energy. So that helps to treat cancer more precisely. For example, cancer in the brain cells, so you can save the brain and kill only the specific places. So how this device works? So this device uses cyclotron. So let's talk about cyclotron. So before we're gonna start, let's say what is the meaning of the name itself. So cyclo is actually a cycle, right? So a circle. And tron is an instrument. And how this device looks. So you have here something huge that look like capital D, and the name is actually the big D, and here D. And remember that this tutorial is actually about a new subject. We finish electricity, and right now moving on to magnetism. So magnetism. So let's draw the magnets, the magnet effect. So here's magnetic field. Here you can see it. I love to draw magnets and magnetic fields with two red. So here what's the X mean? The X mean is say that it's going inside the board. Okay, you see the tail of the arrow, that's the idea. So it's go inside the board. And here these two D's are separated. I have new colors, so let's use them. So they're separated with this some distance D, small d. But in the distance, I have here some voltage. So I know I'm drawing a little bit weird. You see this wave, but I want you to treat it as V0. That's what it is, okay? Some voltage between these two plates, okay? And what I'm actually doing, I'm putting here a proton. Let's call it PT, the proton, and I release the proton. And here the potential is V0, remember? And here the potential is 0. So this is a potential difference. So the first question for me to you is, what is the velocity of the proton here when it finish to go that way due to the electric field? So we don't need this, we don't need this. So I want you to remember, so what's happened to a positive charge? Proton have a positive charge in some field. For example, this pen have a mass, and right now the gravitational field pointing this direction, so I'm gonna leave it, and what's happened? It's accelerating down. So the same thing happened to this proton. So this proton stands still, then it feels the electric field, the voltage, and is falling down. It's actually falling down, okay? So that's what I want you to remember, how you can feel it. So how we calculate these kind of questions in physics 1. Remember, if we had a mass and want to know what is the final velocity, let's write that down. Okay, so the first question is, what is the final velocity of the proton? Okay, so how we did it? We did the energy calculation, right? We said the energy conservation actually. We said that the energy at the beginning must be equal to the energy at the end if there was no dissipation of energy. So the energy at the beginning was only potential energy, right? I'm gonna say conservation of energy, U initial equal to U final, and in the end I have only kinetic energy, right? So this is Vf squared, and at the beginning I had no velocity, but I had a potential, which is qV0, right? This is the potential that I have. Remember that if I want energy, I multiply the voltage by the charge. So this is the idea. And if I'm gonna simplify it, I'm gonna multiply by 2, right, divided by m, put it into a square, I have this velocity. Okay, we found this velocity. And let's go to the next question. So the next question, here the proton is going inside this D, right? And what's this proton sensing? He's under a magnetic field. So the question for me to you is, what's gonna be the trajectory that this proton gonna do inside the big D, okay? The left D. So let's write it down. And what, let's say how the proton will move inside the left D. Okay, and now we're going to talk about Lorentz force. So what is Lorentz force? So you remember that we talked about electrical force. That electrical force was F Q multiplied by E. Okay, and that's going to happen a lot of the times. We're going to talk about some example from electricity. We're going to see that there's actually something really similar in the magnetic subject, but sometimes it's going to be easier doing it as a magnetic idea, and sometimes it's going to be harder. For example, Lorentz is actually an example that make it a little bit harder. So what is Lorentz force? Let's call it Fe, and let's call it Fb. So Lorentz force also wants you to have a charge, okay, and wants you to have some velocity. It's not enough to have a charge. If you are not moving, that thing would not happen. You would not sense this kind of force. And also I want to have a magnetic field, right? And this is not enough. I want you also to have some angle between you. This is the cross. Remember, if the angle gonna be zero between the velocity and the magnetic field, the cross gonna be also zero, right? Because this science of the cross gonna cancel out all these terms. So what we can see here, let's compare the two. So the electrical force wants only the electric field, and it multiply it by some constant, the charge. Here it's not the same anymore. Here I need also to have charge, also to have velocity, also to have magnetic field, and also have this direction. So you see why we actually move up to the next level. That's the idea. Perfect. So let's do the question. So I want to ask what's gonna be the trajectory that this gonna do. And for that, what we need, we actually need the right hand rule. So what is the right hand rule? It's gonna help us. It's really easy to remember. I have some tricks I'm gonna share with you. So this finger is V, the velocity. I remember it. If somebody do something correct, I give him V. Good job, V. So this is V, the velocity. B, I have here a gun, right? So I can shoot at you a magnetic field. So B is actually this finger, and the force if you give somebody a slap, right? So where's the force actually? Here. So the force is actually pointing out of your hand. So this is the idea. Let's draw this here. Finger, 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 finger. Okay, so we said that this is V. This is the direction of B. And the direction of the force is actually, direction of the force is actually going outside of your hand. Okay? Here you can see how it looks like. So let's take this idea, the right hand rule, and apply it here. So if this is the proton, right? So we're taking the right hand. So where is the velocity? Oh, the velocity is going that direction, inside the D. Perfect. Where is the magnetic field? B. Where's the magnetic field? So the magnetic field is actually, it's inside the board. So where the force is gonna be? Boom. It's gonna hit him with this part of the hand, right? So it's gonna move. He was like this, and now he's moving like this. He got this punch, right? And now he's moving in this direction because he got this punch, right? So we have V here. B did not change, right? B is still inside the board. But now, when I'm gonna give him a slap, right? So this is gonna be to here. And this goes on and on and on until I'm getting out of this D. So what is actually the figure that we have? What is the trajectory? It's half of a cycle, okay? So it's really important in this class, in this subject actually, to give you a little bit reminders from Physics 1 about circular motion. So for example here, you can see that this is a circular motion. Perfect. And so let's say how the proton will move inside the left D in a circular motion, right? Half of a cycle, right? So that's what's gonna happen. Perfect. So let's move on to the next question. So the next question is what is the radius of this trajectory? Okay, it's a half of a cycle, got it, perfect. But how big is the cycle? Is huge, is small? So let's find this one out. Okay, so I need this term, okay, in a second, but I can delete this one and this one. Perfect. Okay, this you need to remember it, it's really important, but right now I clean this one up. Okay, perfect. So what is the radius here? R equal to question mark. So how we can find this one? So remember from physics 1 what we need to do? We need to do some balance, okay? We can say that the acceleration, R, the radial acceleration, equal to the sum of forces. And what force do I have? Exactly, I have Lorentz force. So Lorentz force is V as a vector, V, B. And notice that I only did the magnitude and without the cross because I have here 90 degrees angle. So in each time the velocity is in the plane of the board and the magnetic field is actually going through the board and they have 90 degrees angle. So sinus 90 is equal 1. So I can, you know that V cross B equal to the magnitude sinus the angle between them. So this is perfect for me. So it's qVB, and I already know V from this term, right? And what is AR? AR is V squared divided by R, okay? So this is perfect for me because from here I can find what is actually the radius, okay? So if you're gonna clean this one up, so what do I get? I can clean one of the V's, right? This one and this one, and let's put this one here. Not here, sorry. This one here. So we're getting that R1 equal to MQB multiplied by V. Okay, I actually did not substitute 1. I want to show you something. Okay, let's clean this one up. I want to show you something. What we can see, that the radius is actually proportional to the velocity. Okay, what does it mean? If I would enter this cycle with this D with the huge velocity, I'm gonna do a giant half of circle, giant radius. If I'm gonna enter with a small velocity, I'm gonna do like a small turn, right? So that's the idea here. It's really important. Okay, and we already found V, so you can find also R. And right now, what's gonna happen? This one, after you finish half of a cycle, it's gonna get here to this part again. And remember that I told you that this sign of the velocity of the voltage is special. You see, it look like a wave, and wave always changing. So this is the idea here. So the idea is that the voltage always changing. How does it change? It changes with plus and minus. What do I mean? When the proton finish here the trajectory, the half of cycle, and go out, then the voltage change, okay? Shift itself to be a minus sign. And then, what's the proton see? The proton see that, hey, wait a minute, I'm again on the top of the mountain. I see a valley, I can fall through this valley, right? So the next question to you is what is actually the velocity? The velocity, you know what? Before we're gonna do it, I jumped a little bit, but I want to show you something really important. So what's gonna happen is that this proton gonna see the new voltage and would want to fall again, and now it's going to accelerate even more. They're going to have more velocity. It's going to accelerate again. And then you're going to do another cycle, and then I'm going to switch the voltage again, and going to fall again. And that's why I'm going to keep accelerating non-stop. But the question is, from me to you, is what is actually the time that I need to tell my computer, my device, to shift the voltage? Each time you need to do it, right? Plus sign, minus sign, plus sign, minus sign. So what is the time? So the question is, how much time? Okay, let's clean the board. Let's clean this. How much time does it take? How much time does it take to finish the first cycle, right? So that's the question. So how we can do it? We know this is a half of a circle, and we know what is the half circle. So delta t equal to half of t, the time that take me to do the period of the cycle. So it's half of it. And how I can find time? If I'm moving in constant velocity, I want you to notice that inside I may be changing the direction of my velocity, but the magnitude stay the same. There's nothing to change or fight my velocity, right? It stays the same. So it's constant velocity. So I can find it by just dividing the area, the distance that I want to go, which is 2 pi r. And remember, the half is outside. This is t of a full cycle, 2 pi r, and I need to divide it by the speed, right? The speed that I'm having. So let's call everything 1. Okay, why 1? Because this is delta t1. Why? Because when I'm going to finish this, I'm going to enter a new cycle with new radius and a new velocity. So I call everything 1. 2 pi r 1 divided by v1. And remember that the radius is actually depending on the velocity, right? So if I'm going to put it here, so it's going to be 2 pi mqb, mq over b, m divided by qb, multiplied by v1, divided by v1. And this one's falling out, right? Another thing I wanted to notice is these two falling with this one, and we finish by this, and these two fall, so we got pi m q b. And what I want you to notice is something really special. I want you to notice that what we got, pi, m, the mass of the proton, q, the charge of the proton, b, the magnetic field. So if I decided that the magnetic field is constant, so all this term is actually constant. How genius is that? Constant n. How genius is that? Look. So each time I'm going to finish the cycle, doesn't matter in which cycle I am, the first, the second, the third, it doesn't matter. Every time I'm going to be dependent on the velocity. It's going to be the same thing we did. And the velocity is going to cancel out. And I'm going to stay only with constant. So I can tell the computer this amount of seconds, this is going to get the units of seconds, flip the voltage to the other side. Okay, so that's the delta t, and that's how much time it's going to take this cycle and actually all the rest of the half cycles that I have. Perfect. And the next question is what's going to be the radius? What's going to be the radius of the second? Here it is. Of the second half of a cycle, right? So let's calculate that one, and it's going to be the same idea how we did it before. What we actually calculated. So let's clean this one. Let's clean this one. So what? Let's write it. What is the radius R2, right? What is R2? Question mark. That's it, simple. Okay, so the second time. So we know from the previous calculation that if we're gonna say the balance between Lorentz force and the radial acceleration, we're gonna get that R2 equal to what? To mqb, n divided by qb, multiplied by v2. So the real question here is what is actually v2? So how we can calculate v2 as we did before? We can say that the energy at the beginning equal to the energy at the end, energy conservation, there was no dissipation of energy, so perfect, let's do it. But right now something has changed. Right now when I'm getting to this point, it's true because they flip the voltage. Right now I'm on top of the mountain and I can fall down to the valley. I can do that. But it's not the only energy that I have. I also have the previously velocity. Nobody took it away from me. It's still mine. So that we need to keep in mind. So we said that ui equal to u final, and ui is actually half mv1 square plus qv0, which this is the new energy that I'm gonna get, and this is equal to u final. What is u final? Only energy, only kinetic energy, mv2 square, right? So that's what we need to solve. So okay, what can I do? I can just take this one out, divided by m, multiply by 2, and I'm gonna get v2 is equal to square root of v1 square. So this would mean that I have the same velocity, right? And the second time, but here I have another additional term, which is 2qv divided by mv0. So you see this term is actually, let's make it larger, this one. So I have another velocity and it's larger. And this one can go here, and we solve the question for the radius. Perfect. How much time gonna take the second cycle? Second cycle gonna take the same thing. It's gonna take delta t1 equal to delta t2 equal to delta t, which is a constant, and we said that this constant equal to pi m q b. It's gonna take the same time. I agree with you that right now I have a larger, you see, a larger arc to do, which means I have a lot of distance to go, so expect, hey, it should take longer, but I have a bigger velocity, so it's gonna compensate on the large distance that I have, so the rate gonna stay the same. So I'm gonna stay with the same time. It's gonna take me the same time. Okay, perfect. And let's move on. So I want to, do a small refresh to give you a little bit refreshing ideas from Physics 1 about circular motion. So this is the reason I decided to do a section on this as well. So the next question is actually, what is the angular velocity of this of this cycle motion that we have here, right? So let's clean this one also. Clean this one up. Okay, so I'm gonna just do the draw here. So we have here the D's, the Proton that go in here and do some circular motion. Then you do another circular motion with bigger radius, then do another circular motion, bigger radius, another circular motion. That's what's going on. And inside the D's, let's do the D's in red. Inside the D's, there's a magnetic field. That's the question that we have. Just a reminder. I need that as smaller drawing. So what is the angular velocity? What is the angular velocity? Okay? So, what is the angular velocity? Just a reminder, what is the definition of the angular velocity? Is how much angle, that's the idea, angular velocity, how much angle do I do in some amount of time? So, is the change in angle, how much angle did I accomplish in this amount of time, dt, okay? So let's calculate this one in our case. So let's do a general case to find what is omega. So we can say that the biggest change that I can have is, for example, do 2 pi minus 0, the biggest change in the angle, and what is the time that equivalent to this. So this is a time of a period, right? For any circular motion, this is true. So this is going to be 2 pi over t, a reminder from physics 1, okay? And in our case, we already know what is t. Remember, we calculated. We said it's the distance, it's 2 pi r, the distance, divided by the velocity. And we found r already. It's always it's a 2 pi v multiplied by r, which r is equal to we have it here, r equal to mqb, mq divided by b multiplied by v. So v cancel out, and what we have here, and the 2 pi, see that this is divided by that, the 2 pi can fall apart, and we have it in our case, omega equal to 1 over g. So it's 1 over mqb, which means b over mq. Something is not right here. Let me check it. And so this was r. Here it is. Maybe I didn't put the right r. This is r. Sorry, this q should be here. This q should be here. So this q is up here. Now it's correct. Sorry for that. Okay. And what we are getting again, that omega is actually constant. It is also constant. So the rate of the angle that I'm doing is always the same, no matter which cycle I am. The first half, the second one, the third one, the fourth one, it's always the same. And I want to remind you what is the idea of angular velocity. Angular velocity, the idea is to understand where I am in this period, how much I finish. If I'm working with atoms, small atoms, so looking and how much this electron moves and how much it succeeds to doing, and it's 2 cycles, 3 cycles, it's gonna near the finish one. And if somebody else, okay, investing the stars or something like that, the earth moving around the sun and stuff like that, you understand how much angle did the earth did and how much angle left and need to calculate and have to complete the cycle. So the idea is that you can compare where I am on the cycle. So this idea of angular velocity, and then you can compare different cycles and periods, and without the velocity itself, just to understand where I am on the cycle. Did I finish? 2 pi. I'm in the middle, pi. Okay, so this is the idea. And so we getting here that the rate is constant, which make sense. Why? Because the time that I have to do half cycle is always the same. So the time here is always the same, always the same. So if I'm gonna look at the proton, I would move my head with the same velocity. This is omega. With the same velocity, I would not change it. It's always gonna be the same. I can agree with you that, you know, we have this part, which actually the electron, the proton actually accelerate, but let's say this part is really small. So when I'm gonna look at the proton, I'm gonna see that, okay, always the same, always the same, always the same. Okay, that's the idea. And now to my final question to you is, in this exercise, is what is gonna be the velocity when I'm gonna get out of this device? What do I mean by that? Think about that eventually I'm gonna have such a big radius that I'm gonna get out of the device itself, right? And I'm gonna head to the tumor. That's the idea. I'm gonna accelerate this proton, accelerate, and then go out to the tumor. So let's remind you. So how I can calculate the final velocity? So v final equal to question mark, the last one, the biggest one. What's gonna be like? So you know, I can do the energy conservation idea. Another time, it's gonna be a little bit exhausting, and maybe we can give it to a computer to do it, but we can do something really easy. Let's look at omega again. Omega that we already calculated. Let's look at it, and we said that this one is equal to d theta dt, and let's multiply each side with r. We can do that one because it stay equal if I want to multiply by the same thing, dt. And what is r d theta? Remember, if I have here some arc, and this is r, the radius from the arc, and this is some movement in the angle, so it's actually this distance, it's dl, right? So dl over dt, how much this is moving, if dl is really small, right? So this can be taken as the proton moving, so this is actually the velocity. So this term is actually the velocity. So I know that the velocity each time changing in this manner, it's r multiplied by omega, right? And if I want to find the last velocity, the final one, I just need to put the biggest r that I have, the size of the device itself. So if we're gonna do it, I'm gonna get that v final equal to the big radius. Okay, let's say that if this is the d, so this actually this r, it's the final d r multiplied by omega that we already calculated. It's qb divided by a, right? Yes. Okay, let's give you some number. Okay, let's feel a little bit, this is gonna be a little bit more intuitive. So we're gonna tell you that the radius of these devices is around 18 meters. M of a proton is 1.7 minus 27, really light kilogram. Q of proton is the same one of electron, but with positive sign, 1.6 minus 19, and B that I use is huge B. Okay, huge magnetic field, it's 0.46 Tesla. And why I said that it's huge? Because Tesla, it's a gigantic unit, okay? So it's really a huge magnetic field. So calculate this one, let's see what we have here. If you have some calculator with you. If no, I'm gonna let you know the result. So the result is 8, a little bit, approximately 8 times 10 to the 8. What the fuck? What I can say about this size is, yes, it's stinky, it's unreasonable, right? Why? Because this one is bigger, it's twice, more than twice the amount of speed of light, c, right? 2.9972 and go on, 10 to the 8, right? So this doesn't make sense. Why this has happened to us? The reason is that this device is so strong. I can accelerate the proton so much, okay, that they're gonna get to 7% of the speed of light. And then I need to take into account all the relative perspective of Einstein about what's happened when I getting closer to the speed of light. And this is not in the material of the class. I just want to give you a sense how fast we can accelerate proton use Lorentz force. So that was the first question that I want to give to you. You are welcome to read more about proton beam therapy. It's super cool, and it's actually using Lorentz force to accelerate the protons in order to fight some tumors, usually in a brain cell, usually a brain cancer. So good luck, guys. Let's move on to the next question. Hi guys, so the next question is gonna be also about Lorentz law, but right now we're gonna take care of beams. So let's look at the question. We have an automatic door, and let's draw our door. The door is in the universe, so let's do the axis. So we have here X, Y, Z, and in location A, we have this door. This door, start on A and at B, and each part of the size of the door, the area of the door is L by L, which means the distance, this distance is L, and the height is also L. That's the idea. And in this world I have a magnetic field, okay, which is going in the y direction, only in the y direction. And how this magnetic field behave is changing in x, okay, in each x I have a different magnetic field, but they're always pointing at the y direction, okay? So it's changing at x, it's a vector, it's some magnitude, b0, divided by my location at x, and it's gonna be at the y direction. So this is the magnetic field that I have, and in my frame, this is the frame of the door, okay? I have current, which is I. That's the idea. Okay, that's the idea, that I have here some current and it's moving in the direction. Okay, so the first question I want to ask, okay, let's put this one aside. Perfect. So what is the force that you have due to Lorentz force, the magnetic force, on a beam? Okay, so what is the force on a beam? Okay, so if I have this kind of beam, never mind if it's not straight, okay, this beam, and I have some current, let's say, let's draw the current, this is the current I, and in my universe there is some magnetic field, never mind what is the direction of the magnetic, it can be crazy as I would like it to be, some magnetic fields. What is the total force that this beam actually sense, okay, extract to? So how we can solve it? We can take part of the beam, say some part dl in its size, okay, pointing with the current, let's do it pointing with the current, let's do it a vector. So it's pointing with the current. And what is the force only of this small piece of the beam? This is dF. dF, differential of force, is equal to what? Remember Lorentz law? Lorentz law said the Q, the charge, Q, the velocity, let's do dQ, right? It's a small part, dQ, velocity cross B, the magnetic field. And what is V? If here I have some charge, right, that's moving, so what is V? V is dl over dt. It's this distance that this one is doing. It's changing his location, right? So V is dl over dt. And this term look familiar to you? What is dq over dt? This is actually the current. Yes, perfect. So it's I multiplied by, I left with dl cross B, right? And what I left with, okay, what I want to find, not dF, not the small force that this small charge in this location feel. I want to find what is the total force that apply. So the total force, F on a beam, is actually, I need to do the integral. I is a constant, I can take it outside of the integral. I integral, okay, of dl cross B. Okay, this is the idea. And in the case that I have a constant magnetic field, and the beam is straight, okay, and the sign here is the cross product is actually 1. The angle of the cross product is 1. This is the simple case, F equal to BIL. Okay, this is a really, let's put it here. F equal to BIL. Bill, that's our method. I think about some kid named Bill, and he has some beam in his hand which is straight, and there's constant magnetic field in the wall. So this is a really famous equation you're gonna need in the exam probably. It's coming back each year. Okay, so this is really important. This is the general case. We're gonna do in this tutorial a little harder problem than that one, but because we have a changing magnetic field, but this is the simpler case. We're not going to talk about it, but I want you to notice that the force on a beam, the general case, the general term, is the current integral on the beam. I'm going to do the integral on the length of the beam, and I'm going to do a cross of each dl to B, the magnetic field. Perfect. So we found that one. Let's clean the board a little bit. Here it is. So let's clean it. This one. I don't need this one. So we found the general term for the force, which is this one. Right? Perfect. Let's clean it. Okay, so the force is F equal to I integral dl cross B. Okay? And I want to ask you what is the force on the frame of the door. The door. Okay? So I know that every time we play a guitar solo, if it's a really complicated guitar solo, I'm going to divide it to parts. So we can divide the door also to parts, and it's going to be easier for us to determine what is the force. So we're going to call this one up, this one right beam, left beam, and the down beam. Okay, each one. So let's start to calculate. So the first beam, let's start with the right one. Okay, Fr is equal to what? We just said what's the formula? I integral dl cross B. Okay? So let's try to say which one is what. I is given, so this is okay. dl is a small movement in the direction of the current. So dl I can treat it as dx. In which direction? The direction z. Right? This is dl. And what is B? B on this beam is always this, right? But on this beam, x is a constant, right? So it's B0 divided by A, not x, A, because it's a constant here, and y, it's only pointing at y direction. So perfect. Dx, okay, so what I can do, and this one is a constant, I can take it outside, I B0 divided by A, and I have integral on x, right? And z cross y, what is equal to? Let's do the famous cross cycle. So z cross y gave us x, right? Z cross y gave us x, but because we go in the other direction, it's a minus x. So I know that here I'm gonna have minus x. And what are the limits of the integral? What is the lowest value of the integral? The lowest value is actually, the lowest value, wait a second. Sorry, it's not dx, it's dz. Don't know why I did here dx. Sorry for that. This is dz, and this is also dz. It's a small movement in that direction, right? This is dz. Okay, so what is the smallest value that I have? Is 0. And the highest one is L, right? So this is actually equal to I B0 L divided by A at the minus X direction. Perfect. Okay, so we did this one, perfect. And if we're gonna do not the right one, the left one, what's gonna change? Let's see what's changing. I can clean this one up. So right now this one gonna be again dz, but it's gonna point at what direction? At the minus z, right? Because the current is go in this direction, so this is gonna have a minus sign. This term b0 not gonna be anymore a, it's gonna be b. So this one need to be changed to b, right? So then result is b, and this term is gonna have a plus, and the integral gonna be the same. The lowest value gonna be 0, the highest value gonna be L. So we're gonna get this term. So we found FR and also FL left, right? So let's move on to the parallel parallel beams with the x-axis, which is u and d. Okay, so let's clean this one up. So we're gonna stay with the same equation. So let's do fu, f up equal to idlb. What's the L gonna be? If I'm taking this one, it's gonna be movement of dx, right? dx, and which direction? Positive direction. B is gonna be b0 divided by x. Look, be careful. Now the magnetic field is changing, right? It's decay with x. In this point I have a really strong, let's do it in the right direction, a really strong in the y direction, and then as long as I move with the x, I see some decay. You see the magnetic field decay. So I need to put here the x, right? And the direction always gonna stay the same, y. So this is a classic for the circular, right? So it's x, y give us z. So the value is gonna be in the z direction. B0 can go outside, so it's I B0, right? And I B0, and I need to do the integral. Let's do the integral. The integral is 1 over x dx, gonna be at the z direction, in the z direction. And what is the limits of the integral? So the limit of the integrals are, what is the lowest value? It's a, and the highest value is b. Okay, this is good. And do you remember what is the integral of 1 over x? Ln. So we have here I b0, okay, and multiply by ln of what? Ln of b minus ln of a. And using the ln laws, I know I can take this one and write it as ln b over a. So the result is f up equal to IBFS IB0 ln b over a at the z direction. And I want you to notice what's gonna happen. Let's do it in blue. If you're gonna not do the up beam, the lower beam, so DL is changing. It's right now in the x direction, and everything else stayed the same. You see it? Nothing changed. This is the lowest value, this is the highest value, B is changing, everything the same. So the only difference is that FD is equal to minus IB0 ln B over A at the Z direction. Okay, perfect. So we found all the forces applying on the frame of the door. The only thing that left for us is sum them up. I want to know what is the total force on the door. So let's calculate that. So F total equal to FL, let's do to the sum of the forces on the frame, which is FL plus F right plus F up plus F down. Okay, we immediately can see that F up and FD cancelling out, so we can neglect this term from here. And FL and FR, we know them. FL, they're actually IB0 multiplied by L, right? And each one of them have a different dominator, which one have 1 over B, one is B, and the other one is 1 over A, and they both in the X direction. So I can clean this one too. So this is the total force. So this is F total. And now I want to ask you, in which direction the door gonna open, right? The door is moving. This is the door. Where it's gonna move? This direction, this direction. I see it's gonna move in the X direction. So I want you to remember that B is bigger than A, right? Because B equal A plus L. So which means this term is smaller than this one because I divided by a bigger number. So for that reason, this is negative. So the door is actually going to open to the negative side of x. Okay, so perfect, guys. And what's happened today is we talked about Lorentz force, and Lorentz force is really similar to the electrical force that we learned before. It's a little bit more complicated. We did two kind of different exercises. The first one was dealing with the changing of the direction using the right hand rule, and the other one was this about what's happened when we talked about beams. So I think this is the most relevant question that you have. Sometimes there's going to be a question about some equilibrium forces that also can happen, but this is the most general question that you will see. Good luck with the homework, and see you next week. We're gonna learn a new method how to calculate the magnetic field. Like we had Gauss law, now we're gonna have Ampere's law, which is the parallel subject in the magnetic fields. Good luck and see you next week, guys.